Hello and welcome. My name is Nick Lyle. I'm the lead trainer at Waterloo Hydrogeologic. In this video, I'm going to be talking about the PEST workflow in Flex. This is going to be a practical guide to what all the workflow steps are, as well as a bit of a talk on some of the common points of confusion or other points of difficulty that a lot of modelers run into while using Flex. I should note before I jump into things that in Flex version 10, the PEST workflow will change quite a bit. However, most of the points that I'll hit will still be very much valid in Flex version 10, even though the workflow will look slightly different. Before I jump off into the PEST workflow, though, I want to talk about the model that I'll be using for this example. So this is a regional groundwater model. This is a steady state groundwater flow model. The region that this model simulates is about 15 kilometers by 15 kilometers. And if we were to go to the numerical run step, we can take a look at the groundwater flow parameters. Broadly, this model has 6 different hydrostratigraphic zones. In the top zone, we've got this overburden layer. There's a thin contact zone that's relatively high hydraulic conductivity, and which is also where the pumping wells present in the model are strained. And there's also 4 hard rock layers underneath them. If we were to take a look at the hydraulic conductivity, we can see that for the zones, the hydraulic conductivity has been applied homogeneously. In each zone, the Kz is a factor of 10 smaller than the Kx and Ky. In the overburden zone, as well as zones 3, 4, and 5, the Kx is 10 to the negative 5th. In the contact zone, the Kx is about 10 to the negative 4th meters per second. And in zone 6, the Kx is 10 to the negative 6 meters per second. If we go to the boundary conditions now, we can see that there are some river boundary conditions here representing some small streams. There's also these pumping wells here, which are all located in about the same area. These pumping wells have a combined pumping rate of about 250 gallons per minute. There's also been a recharge zone applied homogenously to the top layer, and on the bottom layer there's a constant head boundary condition that was interpolated from field data. This model has already been ran and is convergent, so that's an important first step before using PEST, is that you need to have a running model that's relatively stable and produces plausible results. If I was to go to the translate step and look at the solver settings, we can see that my head change and residual criteria are both relatively precise. These were by default 0.01, but I changed them to 10 to the negative 5th meters. The reason I did that is that when calculating the Jacobian matrix, it's important to have as precise results as is practical, and hence I had to change these parameters for the solver. If I was to look at the results and go to the calibration dashboard, we can see that this model is actually already pretty well calibrated, especially considering how simple our hydraulic conductivity parameters were, although we can see down here that when the observed head was relatively low, it appears that we're predicting hydraulic heads that are too high. If we go to the view map step, you can see that on layer 7, where we've got a lot of observations in a relatively low hydraulic head area. These have a positive residual compared to other layers, say layer 3, where these residuals appear to be more or less uncorrelated. In this model, we have nearly 100 observations. So if I were to select this, we can see all the wells where we have observations for. There's, I believe, 98 of them, which of course is an important first step before using PEST. You need to have observations. With that out of the way, let's open the PEST workflow by selecting Select Run Type and PEST Run. This will open a separate tab here, which we can just click on, and we're at the first step, the Define Observations step. In this step, you choose which observation groups that you want to use and can optionally enable or disable individual observations. So if I wanted to disable a given well, say it was a dummy well or I didn't trust the observations here, I could simply toggle it on or off just by selecting the checkbox. You save changes to settings by pressing the Apply button, and I can move on to the next workflow step, the Define Property Parameters step, just by hitting the blue arrow. The next step is to choose which parameters I want PEST to adjust. As of Flex 9, your options for this are Kx. You can choose Kz, so hydraulic conductivity in the vertical direction, or you can choose the storage parameters. Keep in mind that as Flex 9, you cannot calibrate KYs using PEST. That said, by default, the flow engines assume that the hydraulic conductivity is isotropic in the horizontal plane, unless you've specified otherwise during the translate step. So if you're assuming that the horizontal hydraulic conductivity is locally isotropic and you haven't enabled anisotropy for your model runs, this won't cause any artifacts when using PEST. Because this is a steady state model, the storage parameters don't matter, they don't affect the result. However, I would like to make sure that the hydraulic conductivity in the z direction always remains 1/10 of that in the horizontal directions. In order to do that, I will select use next to kz here, so that adds it as a parameter, but I'm going to say that it's tied to kx. So this means that the ratio on a cell-by-cell basis of kz to kx will always remain the same when PEST is adjusting these parameters. Now, because I've made changes, I'll hit the apply button here, and now my changes have been applied. The next step is to define the pilot points. Pilot points are one of the most common sources of confusion when using PEST and Flex, and I think a lot of that has to do with the name. A better name for pilot points might be interpolation nodes. The pilot points are the places in the model where PEST will actually estimate a value for the parameter, and it's from these points that that value is then interpolated to the rest of your model. As you will see soon, it's not realistic to expect PEST to make an estimate for every single model cell in your model. The reason for this is that if you're using no regularization or Tikhonov regularization, each pilot point that you define means an additional model run every time that PEST does an optimization iteration. And that bears repeating. Each pilot point that you define, if you're not using SVD assist, means a much longer model run. That doesn't mean that you shouldn't use a lot of them, but it does mean that there are practical limits to the amount of pilot points that you can define. These pilot points are just XY points. So if I was to open up the 2D viewer, you can see I've defined 6 pilot points already. This is for the 6 different zones. If I enable the view of the pilot points for zone 1, you can see I've just sprinkled them around within the model area. And as I've already mentioned, the parameters, so in this case, the horizontal hydraulic conductivity, will be estimated at each one of these points and interpolated out. If you only have one point in a zone, then that zone is homogeneous, so there won't be any interpolation, and Flex will just change the property parameters for that zone as a whole. Another important thing to keep in mind is that you can use the same pilot points within a zone, but you cannot reuse pilot points between zones. So if I assign the zone 1 pilot points to zone 1, I could not later assign them to zone 2. With that out of the way, I'm going to start assigning my pilot points. So I'll just select my pilot points for zone 1 and press the blue arrow here, and I want to assign it to kx and kz, and I'll do the same thing for zones 2, 3, 4, 5, and 6. With that done, I can now move on to defining the Kriging variograms. In the define Kriging variogram step, you define exactly how parameters are interpolated from the pilot points. You can read about all the different Kriging parameters yourself in the documentation, but one that I wanted to call a special attention to is this alpha parameter here. The alpha parameter basically defines the range of the variogram, so it's how far out the parameters will be able to be interpolated. If it's set to be too low, you'll commonly end up with bullseyes in your final calibrated property parameter field. In general, it's recommended that this alpha is between 20 and 70% of the longest dimension of your model. In this model, it's about 15,000 meters in both directions, so I'm going to set this alpha to 7,500 meters for all of my variograms. Once I finish this, Flex will calculate the variograms for all the different zones, and I can move on to the select run type step. In the select run type step, you can either move on directly to parameter estimation, or you can do sensitivity analysis. So if you do sensitivity analysis, your model will be run one time for each pilot point that you define, that is for each parameter that you want to estimate, and PEST will calculate how sensitive the objective function phi, or basically the sum of squared residuals, is to each individual parameter. This is a necessary step for SVD assist, which I'll describe very shortly. So I'll select parameter estimation, and there are three options here. Either you can choose no regularization, which is exactly what it sounds like, you move directly onto the PEST run, or you can choose Tikhonov regularization or SVD assist. For Tikhonov regularization, you add some additional constraints to the PEST run. One of those constraints could be a preferred value. So you're telling PEST that you want it to deviate as little as possible from the original parameter values, or you could have preferred homogeneity. So in that constraint, you want PEST to add as little heterogeneity as necessary. There's also SVD assist. SVD assist uses the results of the sensitivity analysis and allows you to combine parameters together and do what are called superparameters. So oftentimes you'll have many more pilot points than you have observations, which is guaranteed to cause non-uniqueness. So using SVD assist, you can cut down on your number of pilot points. Also, SVD assist can actually shorten the length of your runs. With no regularization or Tikhonov regularization, each PEST iteration will require 1 or 2 times the number of pilot points that you define. So in this instance, I think I've got 68 pilot points. So each iteration will take 68 or 136 model runs, which you can imagine might take a very long time. With SVD assist, your number of model runs is proportional to your number of superparameters. So if you only have 5 superparameters, then you'll only have 5 or 10 model runs for each iteration. For this PEST run, I'm going to select Tikhonov regularization. I'll select generate Tikhonov regularization, and I'll select preferred homogeneous. It's generally not recommended to use preferred value unless you've got a good reason to suspect that your initial values are very close to the ground truth. Flex has generated my PEST control file, and I'm now able to move directly onto parameter estimation. All I need to do now is click Run PEST, and PEST will start running. For each optimization iteration, it will tell you what the current value of the measurement objective function is. This is this number right here. PEST will try to decrease as much as it can, and it'll also tell you how many times that your model has been run. The number of times that the model gets run is equal to your number of pilot points or your number of superparameters, or in later optimization iterations, it will be twice that number. And now all I can do is wait for PEST to finish. The PEST run is now finished. PEST lowered the measurement objective function as low as it could get it. And as you can see, it halted because it went through 3 optimization iterations without improving the measurement objective function phi. There are 1,800 total model calls, and I believe the overall time elapsed was about 4 hours, which is not atypical. I can now move on to analyzing the results, and I can either just read the output here, which is essentially just the text showed in the terminal, or I can actually just export all those results to an Excel spreadsheet by pressing the export button here, and I'll open this when finished. I find that this is a much more practical way to analyze PEST results. Now I have the PEST results Excel spreadsheet open. So this was generated by Flex, and I find that anytime that I do a PEST run, I always want to look at the spreadsheet. It's got quite a lot of useful charts and other information in it. The first couple tabs are the calculated versus observed values. There's also a chart of the residuals. As you can see for the different observation groups, it will show you what the residuals are. There's also a table and a chart for the parameter values. So this is just the raw parameter values. So these parameter values here are just hydraulic conductivities. I can put this in a log scale and see how the parameters evolved over time. So we can see that some of these parameters got down to as low as 10 to the negative 12th meters per second, which is probably a bit low. And if I take it off of log scale, we can see that the highest values for these parameters got up to more than 10 to the negative 3rd meters per second, which, depending on which formation it is, may or may not be realistic. There's also the table and chart of parameter sensitivities. This chart shows the parameter sensitivities over the iterations. As you can see in this model, the parameters got relatively more sensitive with time. In general, I wouldn't focus on the absolute value of the sensitivities here, but more of the relative position, as this gives you a sense on which areas of your model are relatively more or less important. when it comes to calibration. The final chart I'm going to show is the objective function phi versus iteration chart. As you can see, this is on a log scale, and this shows the improvement, if you would like, or the degree of history matching your model is able to achieve over the iterations. This chart shows a relatively typical pattern. So there was a relatively large amount of improvement with phi in early time, and it very quickly leveled off. Even in linear scale, the rate of improvement over the late iterations was relatively little. The decline in phi is small, about 50%, whereas in other models, it's common for phi to decline by several times. Now that we've analyzed the PEST results in Excel, it's always now a good idea to analyze the results in Flex. In particular, we want to look at the outputs of the final calibrated model, and we also want to take a look at what the calibrated parameters are in a spatial way. So I'm on the last step of the PEST workflow, and I'll press the Create New Model Run with PEST Results button. This will create a new run, and once I run it, I'll be able to look at the model results. Now that it's run, I'm going to go to the View Map step and view the head results. Interestingly, I've actually got some unrealistic head results here. So if I was to select this on a row view, turn off the layer view, and enable the water table, you can see that Flex actually predicted a water table that's something like 3,000 meters above the top of the model here. There's probably a couple reasons for this. One, there's probably not a lot of observations in this layer, so that this head result only occurred in layer 1, and in an area where there weren't many observations. Probably more importantly, the reason why this occurred had to do with simplifications in the conceptual model. There wasn't any means, so for example, drains or something, for excess water in layer 1 to be removed from the model. And so it was just allowed to pile up in this bullseye of extremely high heads. So this might seem like something of a failed result, but this actually has an important takeaway for me as a modeler. I know that my conceptual model wasn't quite adequate. If I was running this as a real exercise, I might go back and change the conceptual model, for example, adding drains across layer 1, allowing excess water to be removed from the model, and perhaps then I could try another round of automatic calibration with PEST. Finally, I'll take a look at the calibrated parameters themselves. So I'll go to the Define Properties step, and I've already got this all set up and visualized. So I'm looking at the actual KX values, and I've changed the view settings so that this is a log color scale. You can see that the KX values range across the entire model from about 10 to the negative 11 to about 10 to the negative 3. In layer 1 here, which is mostly overburden, we can see that there's a high level of heterogeneity. And even though this model is 15 kilometers by 15 kilometers, I would still note that this is a pretty large range in the hydraulic conductivity values, ranging from about 10 to the negative 9 to 10 to the negative 3. So that's 6 orders of magnitude in what is supposed to be the same hydrostratigraphic layer. And I could continue my review across all the different model layers. I won't go into this in detail, but I'll also note that in the bottom layer, which is supposed to be one hydrostratigraphic unit, we can see an extreme level of variation here. So again, this would be another thing if I was doing this as a real modeling exercise. This would certainly play into how I was calibrating the model and thinking about it. So I've taken some time to improve the calibration of the model, and as you can see, in this calibration, the output heads are much more realistic. We don't have the gigantic head bullseye anymore. The reason why the previous model was so out of whack had partially to do with the fact that there was a pilot point in a river boundary condition, which I moved over. In general, your pilot points should never be in the same model cell as a boundary condition, as this will lead to poor results. Another thing that I changed for this PEST calibration was I changed the flow engine to the MODFLOW NWT engine. In the MODFLOW 2005 engine, as well as many other MODFLOW engines, cells can be turned dry and inactive if the head is below the bottom of the cell. This can cause stability issues, and as you can imagine, in a PEST run where there might be thousands of model runs, each with slightly varying parameter sets, it's quite common for PEST to run into some parameter combination that causes instability, which then causes problems during your PEST runs. At any rate, that's everything that I have. Thank you all for listening, and I hope you learned something.